Well, hello there, everyone. Thank you for the folks who are already there and waiting. Hopefully, y'all can hear me okay and can see what I have up on the screen here. And I can hear myself. That's wonderful. We're going to get started in just a second. So, thanks for hanging out. Hopefully, you guys are all well and safe. And while we wait for people to show up, what I would love to know is one thing you hope to learn. Um, if you have a specific question or concern or something that you're hoping to take away from this, go ahead and put it in the chat if you want. Keep an eye on that. Do be aware there is a bit of a delay in between the when you say it and when I will see it, and then when you can hear me respond. But I will keep an eye on the chat. If you have questions, please go ahead and let me know, and I will do my best to answer them. We're going to be talking have about an hour of stuff to go through. And if you have more questions and stuff as we go along, I don't have a problem staying a little bit later and addressing those. But we'll kind of see what happens. It's sort of going to be like the SATs, where it's going to start at a very basic level, and you sort of hang on as long as you want, and feel free to jump out, and you're not going to hurt my feelings. So go ahead and let me know something you're hoping to learn or something that you're hoping to cover, and we'll get started in just a couple of minutes. Thanks, y'all. All right, I think it's 6:01. I think we can go ahead and get started, or it's something 01 wherever you are in the world. I hope everyone is doing okay and everyone is as safe and secure as they can possibly be. It's been a bit of a crazy 48 hours. So I think we will go ahead and jump in with this. So we're talking about the basic principles of audio analyzers and some related topics, and there's a couple of things that I want to make sure to mention as we jump in. The first thing I want to talk about is that, as you can see, there's a lot of options on the market, and the common thread here is that we're learning the tool set. We are learning the principles at work. So we're learning how to understand what a magnitude trace is. We're learning how to understand what a phase trace is. We're learning how to understand what coherence is. And so for that, it's not so much about... there we go. Max, they just work. It's not just about the particular skin or the tool set that the analyzer is offering you as a user. Under the hood, they're all doing the same thing. And so the skills that you will learn when you understand how to read and interpret this data are going to carry across and be sort of platform agnostic. And with that comes a little bit of understanding of how you like to work with this data, and that sort of will sort of guide you in terms of, hey, what feature sets do I need? What feature set is not important to me? What things do I really want this software to do? And which one of these options makes me, the most comfortable or helps me get my workflow done the quickest? Out of the options that you see on the screen here, RoomEQ is going to get a special mention. RoomEQ Wizard, REW there down on the bottom. It uses a fundamentally different type of calculation under the hood. And so while it can produce a lot of the same data, it gathers it very differently. And there are a couple of things that a live dual channel analyzer can produce that RoomEQ Wizard cannot. So as we get into that, I'm just going to make a note of that as we go so you guys have some sort of understanding of where the similarities and differences lie. And at the end, I will give you a couple of options for ways that you can get started working with analyzer software at no cost to you. We're going to cover that as well, give you a couple free options to kind of get your feet wet. Okay, so onward. The cool thing here is we are going to spend about 90 seconds on math, and then we're not going to deal with math again for the rest of this. And the answer to that is really, the reason for that is because fundamentally we're not concerned with how the analyzer works under the hood. That's going to make you a more powerful user of it. It's going to help you interpret the data, but at the end of the day, our concern is not what the math is doing, it's how do we use the information that the analyzer is providing us. So I'm just going to give you a very, very basic idea of what is happening under the hood of the analyzer, and then we're going to completely forget about that. So all we're doing is the analyzer is taking in or listening to a chunk of sound waves, right? It's taking in a bit of a signal. We use the term time domain or time constant to describe, we use the term time constant or time window to describe the chunk of signal that the analyzer is taking in. And you can see I have a waveform up at the top here. And all it's doing is listening to a bit of the signal, and it's going to do a mathematical operation called a transform, and it takes this data, which is, amplitude over time data, and it is going to convert it to frequency data. So it's just taking the time domain signal that's coming in, and it's showing us what frequency information is contained in that data. And this is actually not nearly as complicated as it sounds. You have all used an RTA on your phone. Here's an RTA. RTA stands for real-time analyzer. We're all pretty familiar with this, even something like the iTunes visualizer or the old Windows Media Player visualizer. If you're familiar with that, if you're old enough to remember that, it's the same thing. The microphone that's in front of me is listening to the sound of my voice right now, and it's breaking it down, and it's showing me what frequencies contain energy in that signal. And that's all it is. So the term for that, so basically this little guy here is what the analyzer is doing. That's the meat of what's happening. And it's called a transform because we're transforming time data into frequency data. And the point I want to make is that this is not new. This is not cutting edge. This is not some fancy proprietary thing. The math behind this was pioneered by Jean-Baptiste Joseph Fourier, or as Jamie would call him, the fancy dresser here. And he was working in the late 1700s. So this idea is 200 years old. And it predates the entire live sound industry as we know it by a good 100 years or even more. And so the idea here is that what's going on under the hood is very simple. It's been established for a long time. There's nothing proprietary or secret about it. It's very basic. If you're an engineering student, you can build an analyzer like this in a spare afternoon. Okay, so that's really all we need to know about what's going on under the hood is, hey, we're looking at time domain data and we're transforming it into frequency domain data. That's it. That's all you need to worry about. So the more important questions are, what can we do with this information? And this is where we start to get into all of the different things that an audio analyzer can do, all the different types of measurements that it can produce, and how do we decide which type of measurement we need to use for a given task. And so you sort of have to work backwards. You have to start at the end and say, okay, this audio analyzer is a tool to answer a question. It's important to remember that this is just a piece of hardware or software that's designed to provide you, the user, with information. It does not make a decision. It's not going to tune your PA for you. All it's going to do is offer you more information and more context, and you are the human being with the brain who's going to make a judgment call, and you're going to make a decision based on the entirety of the information that you have available. So all the analyzer is doing is bringing more information to the table. And so it's really important when you start using an audio analyzer to have a question in mind. What is it that we're trying to learn? If your question is, how long is this table? That dictates what tool we need to answer that question. So, okay, I need a tape measure, I need a ruler, right? How much does this object weigh? The question will dictate the tool that I need to answer that, which is, okay, now I need a scale to get that answer. And so it's really important to think about what you're trying to learn, and that's going to dictate when we move forward what sort of tool we're going to use for the job, what sort of measurement. And so this all boils down to two basic types of measurements. In broad terms, there's a single channel measurement and a dual channel measurement. And everything we're going to look at today in this presentation is going to fall into either of those two categories. And so we're going to start with single channel measurements because they're the more sort of intuitive of the two, and they're the type of measurement that you've already got some familiarity with. So let's talk about single channel measurements. Single channel measurements tell us about the signal, which seems pretty obvious, but you're going to see why I'm making that statement when we get into dual channel measurements. They don't tell us about a signal. Hold that thought. So a single channel measurement simply looks at a signal that's coming in, and it tells us some information about it. So in the case of the real-time analyzer, again, it's looking at the signal coming in. If you look over on the right side here, you see this purple box. That is a single channel measurement engine. In particular, it's a spectrum measurement engine. And you can see there is a single signal meter there. It's bouncing around green. As the level goes up, it gets higher. It's just like the signal meter on your mixing console or in your recording software. It's no different. And so that is the single channel of information coming into the analyzer. It's a single channel measurement, and it's breaking it down into the RTA, which is showing us the spectrum of that signal. I can also show you an SPL meter. Here's an SPL meter, and that's showing the sound pressure level that's being picked up at the microphone. It's the same idea. It's being driven by a single channel of information. It's looking at the signal coming in, and it's giving us some information about it. So, in one case, it's frequency spectral content like this guy, or it's just a number, which is an SPL, which is telling us about the pressure, the acoustic pressure at the capsule of the microphone. So these are all single channel measurements. And if you want to get technical, even this signal input meter is a single channel measurement. So it's just saying, hey, here's what we found. We looked at the signal, and here's what we got. So these are absolute measurements. They're giving us something that is concrete. They're telling us how much 1 kilohertz is in the signal in the case of the RTA, or what is the SPL at this point in space, right? So they're describing the objective signal that they see coming in. So if you're looking for feedback frequencies of an RTA or a spectrogram, that is a great example as well. So a spectrogram is if you simply take this RTA. I'm going to split the measurement window here into two panes. And on the bottom, this is a spectrograph. And you can see that it's sort of the same idea as the RTA, only it's carried forward over time. And if I adjust the dynamic range a little bit, you can see it's functioning similarly. It's at each instant, it's showing us the spectral content of the signal. And it's also giving us a little bit of, it's sort of moving backwards through time so we can sort of see the trend. And so, again, this is a single channel measurement. And if you're looking for something like, hey, I hear something ringing, I hear feedback starting to happen, or I hear a little bit too much low mid in my mix, I want to cut that out. These are really great tools if you're mixing and you want some, a sort of a second pair of eyes or a second opinion on what you're hearing. Single channel measurements are the way to go for that. So, this is the basic schematic of how a single channel measurement works. We start with a signal of unknown origin. We do not know where it came from. We don't know what caused it. It goes through our system. That could be a microphone. It could be a mixing console. It could be an entire sound system. We take the output signal, again, with no idea where it came from, no context, and we perform the Fourier transform, and we break that signal down into its spectrum data. And that's pretty much it. That's the signal analysis flow for a single channel measurement. There's a problem here, and there's a little bit of a trap that you can fall into. And for in the early days of system optimization, when people started paying attention to this, they said, wait a second, let's take a signal called pink noise, And pink noise, when we look at it on RTA, it shows up flat if we average it over a little bit of time. And so the thought was, okay, well, if we send it into our system through our DSP out of the loudspeaker, we pick it up with a reference mic or a measurement mic that has a flat response, and we perform the transform on the data, what we are going to pick up at the other end is not flat. And so the assumption for a long time was, okay, well, we can see where the tonal response of the system has deviated from flat, and we can go in with our equalizer, and we can restore that response back to flat. However, it doesn't work. And so that's why the mainstream system optimization community has sort of gone away from this method and over the last few decades. We sort of stopped doing this in the late 80s. And the reason is it simply doesn't work very well. And here is the crux of the matter. There are a couple issues, but the most serious and the most important issue is this. The analyzer, the single channel process, has no context. It's blind to time. Most of the things that cause response deviations in a sound system are in the time domain, and so we can't fix them with EQ. So we're talking about late arriving energy, we're talking about reflections off walls, we're talking about floor bounce, okay? We're talking about interaction between different systems, the almighty comb filter that we're all very scared of. All of those things are time domain problems, and they need time domain solutions or something like acoustic treatment. Anytime you have late arrivals, it's going to create a response in the frequency domain, but we can't fix it in the frequency domain. And so the problem with the single channel measurement, particularly the RTA, is that it makes time problems look like tone problems. And so it's sort of one of those things where if you have, if all you have is a hammer, all of your problems are nails. And so you end up trying to fix time domain issues with EQ, which can't fix time domain issues. And so that's sort of the fundamental flaw in this strategy. Okay, so for an example, here on the bottom half of the screen is the response of a comb filter. This is when you have two signals. Hopefully, most of you are probably familiar with the concept of a comb filter, but if you're not, a comb filter is this nasty-looking response that is created when we sum two similar signals together with a little bit of a time offset between them. So whenever you have two similar signals that are being mixed together, but there's a time offset between them, at some frequencies, they're going to reinforce each other. At some frequencies, they're going to cancel each other out, or they're going to degrade the response a little bit. And so you get this alternating pattern of peaks and dips called a comb filter because it looks like the teeth of a comb. And what you can see is it's very pronounced on the bottom, which is a transfer function measurement, which we're about to talk about. But on the top, this is the same exact response viewed on an RTA. And it looks pretty mild on an RTA, and a lot of people would be tempted to grab an EQ and put a little boost in there at 250. And that's not going to fix that. Cancellation is not going to go away because this is caused in the time domain. So one of the important things, one of the themes, one of the takeaways, I guess, from this presentation is you have to use the right tool for the job. And if you start using the wrong tool for the job, you're going to end up digging yourself in deeper, and you're going to create a lot more problems. If you're trying to EQ out a floor bounce, you're going to have a long day. Okay, so what do we then do to solve this problem? We use a different type of measurement. When we are not interested in the signal itself, but we are interested in the response of a system that is passing the signal, we take a comparative measurement. So it's called a transfer function measurement. A transfer function is a mathematical term that describes the changes that are imparted on a signal as it passes through a system. And you can go and bury your head in the Wikipedia page for this if you want, but what really is actionable for us in the audio world is it's a comparative measurement, and it's sort of a before and after. So what we can do is we can say, all right, let's take a signal, and we're going to take a copy of that and send it into the analyzer, and then we're going to let that signal go through our whole sound system, and when it comes out the other side, we're going to take a copy of it, and we're going to compare the two. And by comparing the two, we can tell what happened to the signal since we last saw it. We can tell what effect the system has on the signal. So a transfer function measurement is a relative measurement, and it shows the difference between two signals. So if you can think of a sound system as a black box, you can even think of a microphone or a mixing console or a rack mount equalizer, a lot of the devices that we use in audio, you can think of as a black box where we don't know what's going on inside. We don't know what's under the hood. But we don't need to because we can take a transfer function measurement and it'll tell us exactly what's happening under the hood. So if we look at the signal that we're sending in and we compare it against the signal that came back out, we have a transfer function measurement that tells us about the response of the system. And there's an important concept here about system linearity. And we're not going to get down to that rabbit hole too much, but the idea is if you're mixing a show and you turn your master fader up by 3 decibels, you would expect the output of the sound system to come up by 3 decibels as well. If you go to the main EQ on your master bus of your mix and you cut all the low end out of the mix by 10 dB, you would expect to hear the signal coming out of the PA also cut the low end by 10 dB. And so there's a one-to-one stable relationship between what goes into the system and what comes out. We would say that it's a linear system. Now, of course, that's not true if you're running the system into its limiters or you're overloading it or something like that. But in the context of how we're operating these systems, we know that the relationship between the input and the output doesn't change, even if the signal does. So our mix, our musical signals are changing from moment to moment, and that's why when we look at signals on an analyzer, a single channel measurement, like an RTA here, you can see it bouncing around. So this measurement is changing as the signal changes. But if you think about the relationship between the input and the output of a sound system, we have that one-to-one relationship. We have, as the signal going in changes, the signals going out also changes. And so we're talking about how faithfully does this device transmit the signal moving through it. So that's the fundamental difference between a single channel measurement and a transfer function measurement. So this is sort of the schematic for that. This comes from the SMART manual. Thank you to Rational Acoustics for letting me use this. Again, we recognize the center part here from before where we took the output signal from a system, we performed a transform on it, and we looked at the spectrum. However, we have a lot more context here because this time we have an input signal that is known to us, and we've taken a copy of it. And so in addition to a measurement signal, we also have a reference signal. And we can take the copy of that reference signal and perform a transform on that as well. And the analyzer can take both of these in and compare them, and that comparative response is displayed as a transfer function which describes the system response. So we're going to get a frequency response that shows the magnitude and shows the phase. And the really important thing here is that since we have a copy of what went into the system, we also know when it went into the system. And so we can also tell how long it was gone, and this opens up a whole wide range of possibilities about what is our system doing in time? What is the time behavior of this system? You know, we live in a digital world now, and latency is a thing, and things take time. And so we can now make really meaningful statements about the behavior in the system over time. And so that is the data that is displayed as the almighty phase trace. And that's sort of the key to system optimization, because we need to know the temporal relationship of signals and not just their frequency response. Okay, so let's revisit that scenario we looked at earlier where we were trying to use pink noise to figure out some information about the response of our system. So what we're going to do is the same idea that now we have a copy of the input signal and we have a copy of the output signal, and now we have the time that it took for it to move through the system, and with all that information, we have the analyzer compare them. And without getting too mathy, you can sort of think of it as a division problem, 2 divided by 1, or a subtraction problem, depending on how you want to think about it. A good example is that if you have an analyzer with, let's say you have an amplifier that has a gain of 20 dB. And in linear terms, 20 dB is a factor of 10. So if we have like a numerical amplifier and we put in a number 1 and we get a number 10 out, that's a factor of 10. If we then turn up the input and we put in a number 3, we would expect to get a 30 out. So again, we're looking at the relationship between the input and the output. And so 30 divided by 3 gives us 10, and 10 divided by 1 also gives us 10. So we're looking at what the system's doing to the signal by comparing the input and output. So that's the basic concept behind a transfer function. Hopefully that makes some bit of sense. This is a magnitude measurement from a transfer function, and we're going to look at some live transfer function stuff in a second when we get into the analyzer. What you can see is a couple of things. Number one, you're going to read this the same way that you read the RTA response, where you have, the frequencies across the x-axis on the bottom, frequencies, low frequencies on the left, high frequencies on the right, and the vertical scale is measured in decibels. The difference here is you'll notice right in the middle of this scale is 0 dB. And so since the transfer function is a comparative measurement, you can think of this sort of like having the fader at 0 dB on your mixing console. When your fader is at 0 dB, the signal level into the fader and the signal level out of the fader are the same because the fader is not affecting the signal level. And so if we have 0 dB, our measurement sitting around 0 dB, that tells us that the two signals are about equal in magnitude. And you can see there are some areas where it's a little bit higher and a little bit lower. And so this is the magnitude response of the system that we measured. You'll also notice we have a lot more, this is much higher resolution measurement than the RTA. And a lot of RTAs will allow you to increase the banding resolution. And we're going to look at that in a second. But the data from a transfer function measurement is inherently not banded, and we're capturing a lot of data points. And so one of the things that we're going to find useful is to apply a little bit of smoothing like that, because another thing that I hope people will take from this is that we're really interested in the trends here. All of these little things, the kind of little wiggles, these are all sorts of reflections off walls and floors and reverbs and late arriving energy and all sorts of imperfections. And if you move the microphone over about a foot, you can expect those to change. So if you're going to try to go in and fill in these little dips with EQ and cut back these peaks with EQ, you're going to have a lot of problems. So really what we want to do is focus on the trends. So one of the tools that we have available to us in modern analyzers to help us focus on the trends is a little bit of trace smoothing, and it looks like that. And I will show you some examples of that as we go. So another thing that I want to show you, another piece of information that is produced by a transfer function measurement that is taken in real time, and this is a very, very important one for live sound, is this red trace up at the top. This is called the coherence trace. And the best way to think about coherence is a data quality indicator. So if you're doing your monthly finances and you sit down and you add up your budget and you get a number and you say, gee, I hope that number's right. Let me check the math again. And you do the question again, and you do the question a third time, and all three times you get the same answer. Your confidence in that value is pretty high. So you can say, yep, I'm pretty confident that that's the right answer. On the other hand, if you do the budget 3 times and each time you come up with a different number, your confidence is going to be pretty low. And so now we're not really sure what the right answer is because we asked the same question 3 times and we got 3 different answers. So that is sort of a way of thinking about coherence. You'll notice the scale up here on the right runs from 0 to 100. And so for every frequency point in our measurement, for every data point, we have a coherence value. And when coherence is high, the analyzer is saying, yep, we can be pretty sure that we have a solid relationship between the input and the output of our transfer function. The relationship between the measurement channel and the reference channel is pretty good. It's pretty solid. So again, that's, hey, we keep turning that input fader up by 2 dB, and the system keeps turning itself up by 2 dB. So we have a constant relationship between the reference signal and the measurement signal. Coherence is going to be high. Down here in the low frequencies below 63 hertz or so, you can see that the coherence is sitting at the very bottom of the scale. It's sitting around 0. And the reason for that is because of the loudspeaker that I used to take this measurement does not produce information below 63 hertz. It rolls off. So there is low frequency information being picked up by the microphone down here. We can see it on the magnitude trace. But the reason coherence is low is because the analyzer doesn't see a match for that information between the reference signal and the measurement signal. So it says, hey, this doesn't look like what we sent in because we know what we sent in, and we're not seeing a relationship here. The relationship's not steady over time. So what are we looking at? This could be HVAC noise. This could be a really long reverb tail. It's not in this case. This could be a forklift running. This could be noise from moving lights. And, we teach a class in Brooklyn, and every 5 or 6 minutes, the subway goes under the theater. And so you'll see all this low-frequency noise show up on everybody's screens. The thing is that this is energy that is present in the measurement signal that was not present in the reference signal. It doesn't match. And so coherence falls at those frequencies. So the coherence trace is a very, very powerful tool for telling us what sort of actions we should take based on the measurement. So if we go back to the case of the RTA for a second, and you say, wow, I'm seeing this really big low frequency peak at 60 hertz on my RTA. I'm using pink noise, and there's a big bump at 63 hertz. I'm going to EQ that down. Well, you would EQ that down if maybe your subwoofers are set too high, but you wouldn't want to EQ that down if it's caused by an HVAC rumble, or if you're just listening to a bassy track of music, or if there's something else in the space that's causing that noise. And so another way of thinking about this is, can we affect this? Will the changes that we make to our system affect what we're seeing on the screen? And when coherence is high, we have a good shot at that. When coherence is low, we don't. So coherence is a really good piece of information to tell us how well we can trust what we're seeing on the screen and whether or not we should think about acting on it. And so this is one of those opportunities where RoomEQ is a little bit different. The type of measurement that is taken by RoomEQ Wizard is not a real-time measurement. When you have something like Smart or Systune running, it's running in real time. It's running the same measurement over and over again. Smart runs the measurement 24 times per second. And so 24 times per second, it's asking the same question. What's the relationship between these two signals? And so it can say, yep, it's pretty high. It's pretty solid. RoomEQ Wizard, you're putting out a mic and you're taking a sweep, and then your computer sort of goes offline and it processes that sweep. And so the magnitude trace that you're going to get on your screen might look very, very similar. But because the measurement's not taken in real time and it's not repeated over and over again, we're not getting that coherence trace. And so coherence is one of the differences that if you're working with RoomEQ Wizard, you're not going to see the coherence trace on the screen. But we're not done. There's more information produced by a transfer function measurement. So I'm going to take what we're seeing here, the magnitude, and I'm going to crunch it down to the bottom half of the screen, and the top pane becomes the phase response. And so the phase response is sort of the holy grail of system optimization. It's also the part that really scares people the most. And here is the secret about phase response. No matter what anyone tells you, the numbers here are not the most important thing. We could probably not even label this y-axis here. It is labeled in degrees, but it doesn't matter. The only thing you need to know to get useful information out of your phase response in most cases is the slant of this line. You're looking at the trend. So, I mean, you can literally step back 10 feet from the analyzer and squint your eyes a bit and look for the trend. In this case, the trend is, hey, we're tilting down, we're tilting down, we're tilting down, all the way up until about 4K, and then we start to flatten out. So, let's explain what this is. If you think about a clock face for a second, a clock face is circular, and, you know, between 59 minutes and 0 minutes, it's sort of a continuous loop, but we have to break the numbers there to get back to 0. And so the phase trace is the same thing. We are looking at a scale that runs a full cycle. 0's in the middle, 180 degrees at the top, 180 degrees at the bottom. And so if you want to think about cutting this phase trace out and gluing it on a paper towel tube or another type of cylinder, you see that this guy down here at 63 hertz would match here. And so what you actually are looking at is a spiral. So if you sort of took a spiral and you smashed it down flat, that is sort of what we're looking at here. And so this is actually one continuous line, but because degrees and cycles are circular and we're looking at it on a flat screen, we can't really see it that way. So it's important to realize that we are looking at one continuous line that is only broken because we are wrapping it around a display. And once we get down at -90, -120, -150, once we cross 180, we start to come back around the top. It's sort of like the minute hand on a clock. Once it gets down past 6 o'clock, it starts coming back up, but the numbers are actually continuous. So here's everything you need to know about the phase trace to start getting results out of this information in one slide. It's all you need to know. Here we go, right? Understanding the phase trace. The phase trace, fundamentally, it tells us a bunch of things, but at its core, it's telling us about the timing relationship between the measurement and the reference signal. That's it. So, if you have a trend that is downward left to right, like the red line here, that tells you that the information in the measurement signal, the energy is late compared to the reference signal. If you have a trend that goes upward from left to right, like the green line here, that is telling you that the energy in the measurement signal is early compared to the reference signal. And if you have a flat trend on your phase trace, that tells you that the energy in the reference signal and the energy in the measurement signal are in sync. So why do we need this information? What sort of things can happen to cause time offsets in our signal? Well, we already talked about digital latency, and I'm going to show you an example of that in a second when we get into the live analyzer. We also have to remember that it takes time for sound to travel through the air. So if you're 60 feet from your PA system, it's going to take you about a millisecond per foot, or about 3 milliseconds per meter for my friends that are in other countries and use the metric system. It's going to take some time for that sound wave to propagate through the air. So if we simply just set the analyzer up, and we're measuring a sound system that's in a room, we can expect to see the measurement signal is going to be later than the reference signal. So it's going to be really hard to compare them because we've got 50, 60, 70 milliseconds of difference in play there. So the analyzer has a built-in delay mechanism that can delay back the reference signal and sort of bring those two things back into sync again. And that sort of will remove the effect on the phase trace from that propagation delay, from that digital latency, from that acoustic propagation. We can remove that from the picture, and then we can actually talk about the phase response of the system itself. There are other things that will cause the phase trace to be not flat. So like EQ is a great example of that, and we will see that. But in general, what you want to just remember is this kind of seesaw approach that will tell you most of what you need to get started with the phase trace. And that's just about it. So what sort of situation would produce the result where we see the phase trace slanting up from left to right? How could we possibly end up in a situation where the measurement signal is ahead of the reference signal? We have not invented a time machine here. We do not, as far as I know, have any type of PA system that can create the output before it receives the input. That would be a causal, that would probably cause the universe to get sucked into some sort of black hole and implode. So that is not what it is. Remember, if you put your mic out in the space and you're 60 milliseconds from the PA system, we're going to set that delay inside the analyzer, and we're going to delay the reference signal back by 60 milliseconds to match them back up and give us that good comparison. If you then go and you take your measurement mic and you move it down to the front row, you're now closer to the PA, so you have less flight time, but you don't change the delay that you put into the analyzer. You now have a situation where the measurement is getting to the analyzer before the reference signal. So, that's going to be one of the indicators that, hey, maybe you forgot to set your delay, okay? And we're going to talk a little bit more about that, and it's not really something to get hung up on right now. Yes, proposed update on that feature on the Behringer. Yes, the time-traveling PA system. That would be a heck of a show. I mean, really, you could the band could not come out until later if they wanted to. So here is an actual phase trace that I took. This is a measurement of a stage monitor wedge at a festival. And what we can see is this is a really good example because we have all three trends visible on the phase trace. We have a region where it's flat, we have a region where it's tilting down from left to right, we have a region where it's trending up from left to right. And we really can't dig into all the reasons that might cause a phase response to look like this, what is happening mechanically, electroacoustically, physically inside the loudspeaker to cause this response. That would kill all our time just on that one topic, and most of you would probably fall asleep. So for now, we're going to look at how to just recognize these on analyzers. So this flat trend in the middle says that, hey, the frequencies in this range are in time with the frequencies in that range that are in the reference signal. Up here, down here at the bottom where we're slanting down from left to right, that says, hey, the frequency energy in this range is late compared to the energy in the reference signal. And up here where we are slanting up from left to right, that tells us that, hey, the frequencies, the energy in this frequency range is early compared to the reference signal. So those are the three main trends that you need to worry about when you are looking at the phase trace. If you remember those three things, remember that little slide, you are good. So before we get into the analyzer, here are a couple options if you want to get started. So again, Room EQ Wizard is a really popular choice for a lot of people. It was my first analyzer. My first analyzer was Room EQ Wizard running on a busted Dell laptop, and I actually used the microphone that came with Rock Band 2 that plugs in via USB, and that was my first analyzer rig. And you can laugh at it, but it's completely free, and it also allowed me to take real measurements. I used that rig to learn that a certain loudspeaker that we had in the shop, it was a subwoofer, and there was a phase switch on the back of that subwoofer that should have been called polarity, but that's a different discussion. And when I measured both positions of that switch, I realized that switch did not invert the polarity of the subwoofer. And I was able to determine that based on the measurement. And I found out later on that it actually inverts the polarity of the high-pass out crossover jack on the back of the subwoofer. But the idea is you don't need to go out and spend a bunch of money to get started with this. You can get started right now, today, and you can really start experimenting with this stuff and get used to looking at the data on the screen and taking measurements and sort of just get a feel for it. So Room EQ Wizard, as I mentioned, it's not a real-time measurement. So you're going to take a measurement and then the system's going to process it and show it up on the screen. You can take another measurement if you want. You can compare them. So you're not going to get that coherence trace, but you are going to get the magnitude trace, and you are going to get the phase trace, and you can also look at impulse response data. And it's a lot of tools that are really aligned towards small room acoustics. So it's a great tool for recording studios and measuring your living room and look at the decay times and all that stuff. So that is a really good option to just get started taking some basic measurements. Also, a sort of newcomer into the scene is Open Sound Meter. Open Sound Meter is a basic 2-channel real-time FFT analyzer, and that's the same technology that's under the hood as all of the industry standard tools. And so, again, it's a really great way to sort of get used to dealing with taking live real-time measurements. And since it is a real-time dual-channel system, you are going to get a option to see the coherence trace on the screen. So that's another thing to check out. Obviously, it's not going to have all of the full features and niceties and creature comforts that a sort of high-end top dollar analyzer package will have, but it's a really good way to start working with this stuff, and it is absolutely an actionable tool. You can absolutely go out and use this thing in the field and get some information and do your job better. So definitely check those out. And also, there's a bunch of options, and I sort of showed a bunch of them on the screen when we started, but sort of the two main tools that are used in the field that I see, that I come in contact with, are Smart and Systune, and both of those offer free 30-day demos from the website. So you can go to the websites that you see here, and you can download a 30-day demo, and you can try that software out and just get a feel for it. And again, I started off by saying, and I'm going to say it again because we have a couple more folks watching here now, at its core, all of these are providing you with most of the same information. So the skill for reading a magnitude trace, reading a phase trace, that skill is cross-platform. That skill is platform agnostic. So it comes down to finding a tool that works for you, works for your budget, works for the way that you like to work in the field. But any knowledge that you pick up on one of these tools can be transferred to the other tools. So that's the really important thing here. The math that's underlying these systems is absolutely not proprietary. So it's the basic fundamental concepts that I'm really interested in talking about today. So these are a couple options. Okay, so what I thought we would do now is jump into the analyzer and look at some live measurement stuff. I also have some stuff to talk about SPL. If y'all are interested in that, we can come back and definitely cover that. But before people start getting too bored with me, I want to look in and get into some live measurement stuff. So what this is, for those of you who are not familiar with Smart, I'm going to give you just a basic overview of the interface so we all know what we're looking at. So you can obviously see the big pane in the middle is where we actually display the measurement data. This bar on the right is called the control bar, and this is where we adjust the parameters and the settings for the measurements that we're taking. And I'm going to come back to that. But right down here at the bottom, you can see there are these two buttons where we have one rectangle and two rectangles, and those change from a single plot to a double plot. So at any time, we can see one or two panes of measurement data. And I can also come up here and click in the upper left of this pane. Right now it says RTA, and I can change that to a spectrograph if I want. So each pane that I display, I can choose what sort of measurement I am showing in that pane. And it's very similar if you're working with something like Open Sound Meter. It will show you that you can decide how many panes you want to see and what measurement information you want to see in those panes. Okay. On the left here, we have the data bar. And when you capture measurement data in Smart, it goes into this folder. And so you can see I have an archive of previous sessions. And the important thing to realize is that these measurements are very small. They're little tiny files. They're depending on your settings, they're going to be around 100 kilobytes. They're really tiny. And so you can store, I have 3 years of measurement data in my Smart folder, and it's like grand total, it's like 70 megabytes. It's absolutely tiny. So it's really a good thing. It's not like you're recording, tons and tons of hours of high definition audio files or anything like that. You can really keep this stuff and you can refer back to it. And I do find that a really helpful tool, both for increasing my own understanding and a lot of times when I want to go back and show people something. Hey, here's what I measured today. For those of you who are from Reddit, which is probably all of you, I often will go back and show the data that I gathered on a previous job and sort of be able to go through it and explain it. And so keeping that measurement data is super helpful. Over here on the right, again, this is the control bar. Each one of these colored rectangles is a measurement engine. And so each one of those is a measurement that can pull data into the analyzer and can work with it. So you can see that right now, this purple guy, this is the spectrum measurement of the measurement mic that's in front of me. And the two things you want to look at are this colored circle. So the colored circle is showing or hiding the measurement. So if I click the colored circle, I put an X on it, and the measurement's still running in the background, but I just can't see it because I hit it. And if I click it again, it comes back. And the green arrow here will start or stop the measurement engine. When I stop the measurement engine, it automatically hit it, but it's interesting that if I unhide it, I still see that measurement. It's sort of frozen in time. There it is. And then, of course, I can start it again. So I've configured a couple of inputs to my interface, which I've labeled clearly. So one thing I've done is I have a copy of, this is a built-in signal generator, and I have a copy of that signal generator being routed back into my interface, so I can always have a copy of what's going into the system. And this is sort of at the core of that fundamental idea of a dual channel measurement, the transfer function measurement. We need to give the analyzer a copy of what's going into the system. So I call that a loopback. And the really important thing about this is that we are not constrained to pink noise. You can use music of any type that you like. You can even use Ed Sheeran if it's an emergency. You can use the band live on stage. You can use your voice, any type of recording. You can use a sweep. You can use whatever you like. The whole idea with a dual channel FFT measurement is that the system doesn't care what's going through it, and it's going to behave. We have that linear relationship. So we are not bound to using pink noise as a test, and we can use anything we want. We do still use pink noise often for other reasons. It's pretty convenient. However, I just want to point that out, that you do not need to use pink noise when you're taking a dual channel measurement. You can sort of use whatever you want. Okay, so, and what I've done is I've set up another tab up on top, and it's a totally different workspace where I can have different measurements. So over here on the right, I have a couple options for the spectrum. I can change the banding. So we're looking at 1/3 of an octave banding, which is probably the most common. So if you go to the App Store on your phone and you download a sort of RTA app, freeware RTA app, traditionally RTAs are 1/3 of an octave banded. But a lot of the modern apps will allow you to use higher resolution banding. So for example, we have 1/6 of an octave, there's 1/12, 1/24, 1/48. That's pretty high resolution data. You can even disable the banding entirely and see the raw data points from the calculation. One shortcut I do want to point out for those of you who are smart users is that the last thing I touched with my cursor here is this banding dialog, and so that still has focus. And until I touch another control or click something else on the screen, since the program still is focused on that control, I can go on my keyboard and press the up or down arrows, and I can run through those settings really quickly and really easily without having to go back to the menu each time. And so that's also going to work for any other drop-down menu that's going to be in the control bar. So that's a really nice tip for those of you who do work with Smart. And the other thing I can do is I can set averaging. So with no averaging, I'm seeing the instantaneous response of the measurement. We look at a chunk of data, we perform the FFT, and we put the spectrum on the screen, and there it is. And we can turn up some averaging. And there's two types of averaging that you want to sort of be aware of the difference. FIFO averaging stands for first in, first out. And this is the type of average that you've been doing in math class since you were a kid, right? You're literally taking the last couple values and you're averaging them together and then you're dividing it out. So it's just a running average of all the previous samples. How many previous samples you can pick, 2, 4, 8, or 16. So if I pick 16, you can see I'm going to clap my hands, and that clap is going to stay in the averaging buffer for 16 measurement cycles, and then it's going to drop out. So you see the FIFO has sort of a jerky look to it because that data sits there, and then it falls out the back of the buffer. The other hand, the other type of averaging we have is down here, and we have options for 1 second up to 10 seconds. And this is technically an integration. The way to think about this is, if you're familiar with how the needle might move on an RMS meter or on a VU meter on your recording console, how it sort of has a little bit of momentum to it, and so it doesn't respond very quickly to peaks. It sort of takes time to adjust to the level, so it's always just sort of gliding between levels. That is this type of averaging. And so that's the sort of integrated measurement that you would also see on something like an SPL meter or an RMS meter on a console. And with that, the data sort of loses weight as it gets older. So you see the measurement sort of, if I stop talking, I'm going to clap, and then you'll see that it's going to jump up, and then it's going to jump back down. So it behaves a lot visually different than a FIFO average. So this is a really good example of how we choose to view the measurement data. And the lens is a big thing. And when we talk about SPL, we're going to see how we choose to view the data is everything to do with what the data looks like. So to demonstrate this, I've done a quick little fun thing. I have created a bunch of spectrum engines here. I have 7 spectrum measurement engines. And I've assigned them all to pull their input from the same microphone. So if I go into my measurement config, you can see that the measurement channel for all 7 of these guys is my measurement mic. So they're all getting the same exact signal. The only difference is if I look at each measurement, I have set each one to ignore the global averaging setting, and I've given each one a different amount of averaging. So I have no average, I have 4, 8, 16, 1, 2, and 3 second averaging. And so what we're going to see is the difference that the amount of averaging will make on the measurement. Another thing I want to show you is in Smart and most analyzers, we can move our view up and down here by using the up and down arrow keys, but we can also offset the data itself. So I'm actually going to literally click and drag this data up, and I'm going to add an offset to it so I can pull it up, and I'm going to pull this guy up. There's the 2 seconds, and here's the 1 second. I'm going to pull this guy up, and here's the 16 FIFO. I'm going to pull him up, and this one, and this one, and finally no average can be down here. And I'm going to hit the minus key on my keyboard. I'm going to zoom out a little bit. So now you can see that how the RTA is displaying the data, the averaging has a lot of effect on how that looks. And so this is one of those really good examples of we're always viewing the data through some sort of lens, and it's important to understand how it's being presented and how the controls and parameters that we pick will make the same data look very different to us, because one of these looks a lot more dynamic. So maybe a lot of front of house engineers that are mixing, they will pick a very, very slow averaging, like 10 seconds, like the pink one up here, and they want to just see sort of the general trend of the energy content and spectrum of their mix over time. So maybe you want a long averaging, maybe you want a short averaging, maybe you want no averaging. I'll also show you a dirty little trick that you probably won't learn if you take a Smart class, because it's generally something that we don't advise. However, if you hover your mouse over the word spectrum up here in the control bar, it turns into a clickable button. It's called a magic button. You open this guy up, and there is an option in the RTA display settings, instead of bars, to display them as lines. And when I hit that, you can see that I've gotten rid of painted in bars, and I'm now just displaying each measurement as a line. And so this looks really cool. However, there's a pretty serious reason that we don't recommend that you do this, especially when you're just learning, if you're just getting your feet wet with the analyzer, especially if you're actually taking a class at the moment. The reason is that this can look a lot like a transfer function measurement, and it's totally possible to configure Smart so you can view both the spectrum measurements and the transfer function measurements on the screen at the same time, and it's really easy to get confused between these two fundamentally different types of data. So for that reason, we advise you, at least when you're starting to work with the analyzer, maybe it's okay to leave that setting off for the time being, but you should know that it is there. Okay, so, and I'm going to split the screen here, and we are also going to look at the spectrogram. And the thing about the spectrogram is this does obey the global banding. So if I pick a higher resolution of banding, I can see that I also have higher resolution data on my spectrogram. I come over here on the left and adjust these little widgets, arrows, whatever you want to call them. These set the dynamic range. So it sets the level at which we will go to our brightest color, and it sets the quiet level at which we'll go to our darkest color. And so when you adjust that dynamic range, you get a very, very helpful view of what's going on in the mix. And so you can actually see the overtones in my voice as I talk. And so this is another really great mixing tool, especially if you tie your spectrum analyzers to the solo bus on your mixing console. And whenever you hit solo, you're going to hear that in your cans or in your monitors, but you're also going to see the spectral analysis of that pop up on the screen. And so if I'm mixing a corporate event or something like that, and I have, lavs in a bad room, and I want to make sure that I don't have anything ringing, this is a really great tool to sort of give you a little visual confirmation of what you're seeing and sort of help you keep tabs on stuff and get to those problems a little bit faster. It's also a fantastic ear training tool. Hey, what's that I'm hearing is a really valid question to ask an analyzer. And so the analyzer is a great way of helping you sort of confirm what your ears are telling you. Now we're going to jump over and we're going to look at a transfer function measurement. I just want to point out before I do that, this bar along the bottom is called the command bar, and it's generally intended for people who are using Smart on like a touch screen or like a Microsoft Surface, something where you have a pen or a stylus, and you're not really using a mouse to navigate. And you can assign these buttons to any function that you want. So if there's a function that you use pretty frequently, you can assign it to one of these buttons, and there it is. I'm going to hide it because I prefer the extra screen space, and I'm always using an analyzer with a full mouse and keyboard. So to me, I don't feel the need to have them on the screen, so I'm going to go to View, and I'm going to unshow. I'm going to hide the command bar. I'm going to go back to our default tab. And so one thing that we're going to do is we're going to click down here at the bottom where it says Transfer, And now we have transitioned the analyzer over to transfer function mode. And you'll notice that the controls that I have available to me on the right have changed as well. This no longer says spectrum, and now says transfer. And I have some parameters I can choose for my transfer function measurement, and I have a couple of transfer function measurement engines prepared. Notice that each one of them now has 2 input signal meters. And that's because the transfer function measurement, as we talked about, requires both signals to work. You use the little R and the little M for the measurement and the reference signal. So I have a couple of transfer function engines set up. We're going to start with something very simple. The audio is coming out of my interface. It is passing through a Symmetrix Prism DSP, which is my DSP of choice for a lot of the work that I do. It's sitting here on my desk next to me, and it's going through just a basic loudspeaker processor inside there. I've got some EQ, I've got some delay, I've got some shelving filters, so on and so forth. And then it's going out to a near-field monitor that is just on my desk that I use for everyday listening and stuff. And so the first transfer function that we're going to look at is a transfer function of the DSP. So if I open up the transfer function, we can see what I've chosen for an input and an output signal. You can see that my measurement channel is the output of the DSP, and my reference signal is the loopback from the noise generator. So what we're going to be looking at here is the response imparted on the signal by the DSP. So the first thing I'm going to do is I'm going to turn off the speaker that's pointed at my face so I don't have to listen to pink noise, and I'm going to turn my signal generator on. And as soon as I hit play, you can see that on the signal meters here, I have levels on the measurement signal and the reference signal. They're matched. And you can also see that the transfer function measurement is now on the screen. So I have 3 data panes here. On the bottom is the magnitude trace. It's just like I talked about in the slideshow. Above that, we have the phase trace, and it looks angry right now. And above that, we have what is called the live IR, which is the impulse response. And we're not really going to get into that today. It's sort of beyond the scope of what I'm covering, but basically this shows the arrival time of the sound data in the time domain. And so the first thing that we want to look at is, if you remember my little slide on phase and reading the phase trace, we have a downward slant from left to right. So as we talked about, that tells us that, hey, your measurement signal is late compared to the reference. So the first question we need to answer is, okay, well, why is it slanting down more and more at high frequencies? And the answer is it's actually not. This is just an illusion built on the fact that we view frequency response data in our audio world. We generally view that frequency response data on a logarithmic axis because that's how our ears work, that's how our EQs work. So you see every time I go up here, it's a doubling of frequency, it's an octave, it's an octave, it's an octave. So what I'm going to do, I'm going to change the display frequency scale temporarily to linear, and you can see that when I do that, now we're spaced equally linear with frequency, and my phase response is now a solid tilt. The tilt is consistent all the way up. And so whenever we see this, this should indicate to us, hey, this is a linear time delay. There's a delay, there's latency, something is late. Our measurement signal is late compared to the reference. So the trick is to train yourself that when you see this in your standard logarithmic display, that is actually a constant tilt of the phase trace. And so I'm going to capture this measurement, and when I capture this measurement, it's going to go up to this folder that I've designated. I'm just going to hit the space bar, and I'm going to call it DSP1. And now I've saved that measurement, and it's over here, it's red, and I can click it, I can hide it, I can show it, whatever I want to do. So what is causing this? Well, this is a digital signal processor. It has some latency. And so our clue here is that we have this downward tilt from left to right on the phase. So you can also see, if you look at the live impulse response, 0 right here is the middle, and the peak in the energy arrival is actually after 0. So it's showing, hey, your energy is showing up late. And there also is a hint in the magnitude trace. You see the coherence is starting to drop a little bit up here at the high frequencies, and that's sort of one of those under the hood things that we don't really have time to get into today, but there's a couple of hints on the screen once you get used to working with the analyzer that, hey, you didn't set your delay. So to set the delay, I'm going to go over to the transfer function measurement engine over here on the right. I'm going to click Find. And Smart's going to compare the two, and it's going to say, okay, hey, we measured a delay of 1.02 milliseconds between these two signals, and we think that's how much delay you need. So I'm going to go ahead and hit Insert. And voila. So what I've done on the top is now the peak in the impulse response is matched up. It's right in the center. And you can see that the phase trace has flattened itself out because we've removed the effect of the latency on the phase trace. So this is a pretty linear DSP. The other thing I want to point out is that we are operating at unity gain here. The line is flat at 0. And you can see up in the top bar here, this is the cursor readout area. So wherever my cursor is located, it's going to tell me some information about that. So you can see that it's only less than a dB down through my whole measurement loop. So if I were to turn up or down the pink noise, you will notice that that measurement does not change. And the reason is this is the same exact thing that I was talking about earlier. This is the same exact idea as turning up the master fader on your mixing console, right? The input to the signal system goes up, the output to the system goes up. They're linear. The relationship between them didn't change. So we're still sitting at 0. The transfer function hasn't changed. Okay. If I go into my DSP, however, and I turn down or up the input to the DSP, I'm going to turn the DSP down by 6 dB. And now we can see we have an offset here because the output signal is now louder than the input signal. And I'm going to put that back. What if I turn down the output signal? Here we go. Did I flip these? I wonder. Let me make sure I didn't flip these. I didn't. Okay, we're good. Wonderful. So what we can see is that if we change the gain inside the measurement loop, we can see it on the screen. If we change the gain outside the measurement loop, we don't see it as part of the analyzer. And that goes as well for EQ changes. So one of the things, I know exactly why. I got a little bit ahead of myself here. Sorry about that, guys. All right, so I will now repeat that demonstration, and it will make sense to you this time because I have the setting on from my rehearsal. So I'm going to turn down the DSP by 6 dB, and you're going to see if my DSP wants to cooperate with me. Come on, baby. There we go. All right. Turn the gain down inside the measurement loop by 6 dB, and you see that line went down on the screen by 6 dB as well. And again, I can turn my signal generator up or down. It doesn't matter. I can change this to pink noise. I can change this to a song. It doesn't matter. So that is the idea of a dual channel measurement. So the input and the output are tracking. So I'm going to put my gain back to unity. And we're going to put an EQ filter on. So what I'm going to do is I'm going to go to 2K, and I'm going to put in a minus 10 dB cut so we can see what that looks like. There we are. So what we're actually looking at now is the actual effect of the filter. And so we can see what the EQ is doing to the signal that's passing through it. And as we know, EQs cause phase shift, right? Can't change the signal in frequency domain without changing it in the time domain because they're equivalent to the same thing. And so we see the phase shift of the analyzer up here in the phase response, and we see the effect of the filter over here in the magnitude response. Okay, so I'm going to take that filter back out, and now we're going to take a transfer function measurement that includes the loudspeaker that's here on my desk. So to do that, I need to turn the speaker back on and give it a second to wake up. There she is. And so I am now going to hide this DSP trace for a second, and I'm going to turn on my mic transfer function. And again, I'm going to start with the delay at 0 so you can see what that looks like. So I turn on my signal generator. Okay, so I've grabbed that measurement, and it looks like this. I've called it pre. And again, we can see that, hey, we have a pretty significant slant down from left to right here on the phase trace. So it's telling us, hey, guess what? The measurement signal is late compared to the reference signal. And so we need to add some delay. Why? Because in addition to the latency of the DSP, we're now also going through the loudspeaker and through the air to the microphone. And so there's going to be a little more delay there than we would expect just going through the DSP. So I'm going to put the pink noise back on. I'm going to hit find. And now what I've done, I will hide the previous measurement. And you can see that now above about 2K, we've flattened out that phase trace. So we are now in sync. Our two measurements are properly delayed to each other, and that ended up being 2.13 milliseconds. And you can see we do have a gentle tilt going on down here in the low frequencies. And this is pretty typical of how a loudspeaker functions in the real world. And again, the causes for that are something that we're not going to get into, but this is pretty much a typical loudspeaker. You will notice that where it flattens out, it's actually hanging around 180. So if I'll point this out real quick. I'm going to show you the DSP again. And boy, am I going to mute that. You'd think I would like listening to pink noise by this point, but I do not. So we have a phase trace that is flat at 0. So one thing I'm going to do real quick, just so you can see what it looks like, is I'm going to go and I'm going to invert the polarity in the DSP. And what that does is my phase trace is still flat at 0, but it's now flat at 180 degrees. So we have no tilt. The phase trace is trending flat, and that says, hey, we're still in time, but we are now out of polarity, because polarity can be thought of as putting every frequency 180 degrees out of phase. And I mentioned before how the phase trace is sort of a continuous roll rather than a pane. And if I click in the phase trace and I use the up or down arrows on my keyboard, I can roll the entire display. So now I've got 180 in the middle, and you can see that is what a polarity inversion looks like on an analyzer. And the reason I want to point that out is because if you look at the response of the loudspeaker here, you can see that the high frequency arrivals are in fact out of polarity. And so that is a pretty common thing that is sometimes done in loudspeaker design to make the crossover work well. Again, we're not going to dive into that. If you want to know about it, Ethan Weiner has a fantastic book called The Audio Expert that you should read, and he will tell you why people sometimes do that. So now let's measure this loudspeaker. So if I look at the measurement that I took here, let's look at the coherence. Notice the coherence is really high for the electronic measurement. It's an electronic measurement. There's no noise in there, right? It's pinned across the top. It's 100%. If we look at the coherence for the loudspeaker transfer function, we can see that it starts to roll off a little bit down low, where guess what? That's where the response of the loudspeaker rolls off. So of course, what we're picking up down here, we're not as confident in it. The signal noise ratio is pretty poor. I have some dips that are kind of in the mid-range here, and we have desk reflections and stuff like that. But overall, it's just still a very, very good measurement. We have very, very high coherence across the entire band. So the reason that the trace is a little bit lower than 0 just has to do with the gain structure. So one thing I can do is turn up the gain on my measurement mic. I'm going to turn it up by about 6 dB. I'm going to take the measurement again, and I'm going to unmute my loudspeaker. For those of you who are wondering how I'm turning the signal generator on and off without clicking it, I'm pressing the G key, G for generator. So I take this measurement again. There she is. You can see it's come up higher on the screen because I turned up the gain of the measurement mic. So the gain inside our measurement loop has increased. And that's important. If you start taking measurements and you're trying to level the different zones of your system, and then you go and you turn your measurement microphone gain up or down at your preamp, you got to be real careful about that, because now you can no longer compare those relative measurements. The system didn't actually change in level. I didn't turn the loudspeaker up or down. I just turned up the sensitivity of the microphone. Okay, so that's something you want to be aware of. Generally, when you start working, you want to set your gain to a comfortable level, and you want to leave it there for the entirety of your measurement session. So here is our measurement. And now what we're going to do is we're going to put a little bit of EQ on this loudspeaker. And so here's a cool thing that we can do. The idea with EQ is that we're going to look in really broad strokes, right? We're not going to try to counteract these dips and these little peaks in here. We're going to look at broad strokes. So let's apply a little bit of smoothing to this measurement here. And actually, let me capture a copy of that. So I've called it pre-EQ. And this is what our loudspeaker looks like pre-EQ. And so there we are. So this is the pre-equalization response, and we're going to try to just flatten out the response of the speaker. We want to get rid of this low frequency buildup. And if I take the smoothing off, here's the raw data. And so the trick, one of the things to train yourself on, is to be able to see the trends. We're looking for the forest here. We're not looking for the trees. So the trends are, okay, we have a little bit of a low frequency tilt up here at the bottom. We probably want to try to get rid of that. And we have a little bit of low frequency kind of ramp up at the top. Now, in the real world, I would never make an EQ decision based on one measurement position. I would move the mic around the space that's covered by this loudspeaker. I would take a couple measurements, I would average them together, and I would look at the trends, okay? Just for the sake of demonstration, let's say we're going to go with this. So here's our pre-EQ response, and I can add a little bit of smoothing to it. And that really shows you, as you add more and more smoothing, it shows you the general trends, okay? So I'm going to leave it on 1/24th, which is comfortable for me, and that's about indicative of where I'm working. Another trick that I will use is I will zoom out pretty far in the magnitude display. I'm going to hit the minus key on my keyboard a bunch of times. So I will generally work about here when I'm working in the field. And my feelings are if I can see a trend at this level, kind of at the 10,000 foot view, that's something I'm going to go and work on. But for the time being, I'm going to leave it there. And so what I'm going to do is I'm going to put some EQ filters on. So the first thing I'm going to do is I'm going to go and put a parametric filter down here at about 150. And what I just did is instead of hitting the space bar, I hit this capture all button down here, and that captured both of my currently running transfer functions. You see that I've created a folder over here called the name of the measurement that I gave it, post low frequency, and it captured a measurement for both the mic and the DSP transfer function. So those are both there, and so you can see the effect that that filter had. Now there's a very novel concept here, which is, hey, okay, we're trying to use the cuts to counteract the excesses in the response. So we sort of want this filter to make a mirror image of the general boost trend. And so the idea is, well, instead of doing that, what if we actually flip over the EQ trace? Let's flip it upside down like that. And so instead of trying to counteract the shape, we can just lay it right over the response that we're trying to correct for, and that will let us see how well it's compensating. And that was why my gain line went backwards before, because I was testing that beforehand and forgot to put it back. So if I open up the transfer function measurement engine here, and I open up my DSP transfer function, and I click invert magnitude display, and I hit OK, now what's going to happen when I run that transfer function again, as you can see that it's flipped upside down. So I'm also going to add some offset to that trace just to visually line it up a little bit more. And then what I'm going to do is I can see, hey, maybe I should gain that filter down a little bit more. So instead of -9, there's -12. And so that's kind of flattened that low frequency response out a little bit better. And the other thing that I want to do here is I'm going to use another gentle parametric up here around 7.5K or so to kind of cut back this little excess. And I think that's a little bit too high. And again, the 1 over EQ, the inverted EQ, is a great way to see that. So I'm going to move it down in frequency just a bit. And there it is. And I'm again going to hit capture all. And now if I hide everything except for those two traces that I captured, I'm going to put back on the original response. And I'm going to change its color. And so we're going to look at the original response in, let's see, I like the blue. And we're going to look at the post response in pink. And one thing I do is I always try to use green for my DSP traces, so it just keeps me a little bit mentally calibrated. So you can see now the before and the after, along with the EQ that was required to get us there. Okay, so that is pretty much all I have on live analyzer stuff. If you guys want to keep going, we can jump into some SPL stuff. If not, you're not going to hurt my feelings. I'm going to take a quick break. I'm going to get a drink of water. If you have questions, throw them up in the chat. And those of you who want to keep going on SPL, let me know, and we'll jump in. And if not, I'll talk to you guys later on. Either way, thank you so much for checking it out. And again, here's the slide so you can see some of the options for getting started with an analyzer. And if y'all want to do SPL stuff, I'll be back in about a couple minutes. All right, thanks, guys. All right, ladies and gentlemen, here we go. Let's take a look at some of the questions that we have here. All right, so let's take a look. So real quick, at what volumes do you usually calibrate your system? The really nice thing about this is that, as you saw, I can turn the signal generator up and down, and the transfer function measurement doesn't change, right? So at the bottom of the range, you have ambient noise in the room. Generally, you want to be 10 to 15 dB above the noise floor in the room, which is not very loud. That might be 75 or 80 decibel SPL level. And at the other end, you have whenever you start driving your system into clipping. But until that point, you're going to get pretty much the same measurement data throughout that range. So I will generally turn my, actually, can I demonstrate that? Here's a demonstration. So what I'm going to do is, here's my transfer function measurement. And you can look at the coherence. And what I'm going to do is I'm going to turn the signal generator down. I'm going to stop talking. I'm going to turn the level down and down and down. And you can see the coherence drop as it gets lost in the noise. So at this point, if I talk, I'm going to majorly screw the measurement up because the noise floor, see, it's really struggling. But as soon as you get above the noise floor in the room, the measurement's going to fill in, and it's pretty much going to be stable. The other thing you can do is add more averaging. So if I go to 8 seconds of averaging, my voice is going to affect that measurement a lot less. So the short answer is just loud enough to get the results that I need. As soon as that coherence trace stabilizes it, you're going to get to a point where turning it up anymore doesn't improve your coherence at all. And at that point, you're just looking at reverb and stuff that's causing the coherence to drop. And that's obviously going to get louder as you turn up the sound system. So I will measure as quietly as I possibly can, so I don't bother people. Okay, next question is tons of questions regards to workflow and taste. Okay. If you're EQing a room, what would you use the individual PA spots as references for measurement points? So generally, the on-axis is going to be the representative position for a point source box. I'm also going to look at the edges of the coverage. You take a couple within sort of, a 5 or 10 foot cluster that's in this sort of what Chris would call the meat of the coverage of that loudspeaker. And then you're going to sort of average those, and that gives you a nice target response that sort of will reduce a lot of the spatial variations and stuff. If you're talking about an array where you have multiple elements that have shading and processing, that's a little more complicated. But generally, if the decision is equalization, we're generally going to do that in the center coverage areas of the system. That's, when you get off to the edges, it becomes not representative anymore. If you're looking for a delay or time alignment measurement or something like that, obviously that's a different situation, and your mic placement is going to be in a different place. How many mic positions do I use? It's not as much about the capacity of the room, it's about the complexity of the system. So if it's a point source box, it's going to be a lot less than if it's a line array that has a bunch of different elements and zones that can be shaded and addressed and stuff like that. And generally, I try to do it with as few as possible. And another thing that really helps is with experience, you start to get better at seeing the trend and ignoring the spatial stuff. So one skill that you'll develop is looking at the analyzer and knowing what is spatial stuff that's going to move when you move the mic a foot and what stuff's going to kind of hang out as a general trend. So I think I can show you one example of that. Here we go. This is data that I gathered at the audio meetup that I did in Albany a couple months ago. This is a mic position taken here. This measurement was taken with and without the correction curve for the microphone. So you can see there's virtually no difference if we look at, let me hide that guy. If we look at these two measurements, you can see that there's virtually no difference in the magnitude response or the phase response. So, this is a nice microphone, and that correction curve isn't really doing anything. Then I moved the mic about a foot away, and I got this measurement. So what you can see is a lot of that spatial stuff has moved. So this is why you don't want to try to go in and get these little peaks with EQ. But the general trend of the measurement has stayed the same. And so if you use a little bit more smoothing, it's going to make it easier to see that trend. And the other thing you can do is average a couple of these traces together. You can select them and hit average. And there is your average trace, and that's going to help kind of suppress some of the spatial stuff. But in general, only a couple of mic positions, but they are really important. So when in doubt, take a couple more measurements. It's free. It doesn't cost anything, right? Can you tell by the phase tracer when a subwoofer is in phase but out of time? Yes. So yes, you can. I'm wondering if I have a good example of that in my data here. If I do, I'll take a look for it and we can take a look at it. If not, send me a message later and I'll show you. Trouble understanding how a flawed response in a loudspeaker affects the sound of the speaker. That's sort of a ball of wax that I don't really want to get into. We all have heard of Ohm's law. Ohm had another law called Ohm's acoustic law, and it was a statement about how the phase relationship of the overtones of a sound affect our perception of it. And so there's a lot of research on our sensitivity to phase shifts in a signal. Ethan Weiner has a great piece. If you go to Ethan Weiner's website and do look for his article on phase, humans are really, really tolerant of pretty large amounts of phase shift. The problem is when we start trying to combine systems or combine signals that don't have matched phase responses. That's when you get comb filters. That's when you get cancellations. That's when you get audible problems. But in terms of just a single response that has a non-flat phase slope, that's actually not audible in the amounts that we tend to run into in live sound in most cases. Isn't being in phase and out of time a contradictory statement? The answer is no. It's possible to be in phase but out of time. So there's an old trick to align your subs where you would say, okay, my crossover point's 100 hertz, so I'm going to play a 100 hertz sine wave through the PA and the subs, and I'm going to invert the polarity in the subs, and I'm going to adjust them until I hear the most cancellation, and then I'm going to put the polarity back. The problem with that is, let's say your crossover point's 100 hertz, just for easy math. You have a cycle of every 10 milliseconds, right? So if you adjust the delay on your subs, it's possible to end up with a situation where you have 10 milliseconds too much. So maybe you have 27 milliseconds instead of 17. And so the phase relationship at the crossover point, it's going to be in phase, but you're a cycle late. So the timing is wrong, but the phase is correct. And so you sort of get into this sort of a happy accident. Merlin Van Veen has a really fantastic article and series of videos on his website that demonstrates exactly that effect. So the way that looks on the analyzer, do I have any examples of that? Let's take a look. Okay, I think we can sort of conjure up an example here. So this is sort of an artificial example, but I'll show you what it looks like. So I put a bunch of smoothing on the phase trace to make this easier to see. The reason that this system's... Now, if this is the sub and the mains, you can see the crossover point right here where they are matched in level is about 100 hertz. That's right here, where the levels are matched. And it's only at that point in the surrounding area where we really care about their phase relationship. And if we look... I'm going to zoom in. You can see, and again, it's smooth data, so it's not a good good representation. But the idea is that at these frequencies, they're crossing, so they're in phase. Their phase response is both X number of degrees here, minus 23, whatever that is. But the slants are not the same, and we know that when we have different slants, we have different amounts of time offset. So that's a situation where the red line here, which is the main PA, is a steeper slant down here. And so timing-wise, it's a little bit behind the arrival from the subs, but they are in phase. So that's a situation of how you can be in phase but not in time. And it's not really the best example of that, but that is what that does look like. And so I definitely recommend checking out Merlin Van Veen's article on that idea. Okay, we are going to look at some SPL stuff real quick. Yeah, go ahead and send me an email. I believe there's contact information on my YouTube channel. I should be able to. Also, I'll go to my website, precisionaudioservices.com. It has my contact info there. Go ahead and I'm happy to answer questions. So let's do SPL real quick. So what is SPL? SPL stands for sound pressure level, and it is a measure of how strongly a sound wave will disturb the ambient air pressure, right? So we're fluctuating above and below the ambient air pressure, and for a louder sound, it's more and more of a fluctuation. So you see the Angry Bird, he's yelling a lot more here, and he's creating larger pressure fluctuations in the air. So when we measure that, it's sound pressure level. And we put it on a scale of decibels. At the bottom of the scale, we have 0 dB SPL, and that is used as a reference for the human hearing threshold. So the quietest sound that a human can hear under normal circumstances, we're going to call that 0 dB SPL. At the top of the range, somewhere around 120 dB SPL or so, is the perception of physical pain for a human. So everything you hear in your day-to-day life sort of falls somewhere in that spectrum. It's important to remember that SPL is not a measure of loudness. Loudness is perceptual and has a lot to do with how our brains interpret sound, and also varies a lot from person to person and is influenced by a lot of different factors. Whereas SPL is an objective measurement of a pressure variation. We can measure it with a microphone and put a number on a screen. And so although SPL doesn't directly describe loudness, they're fairly closely related, and so allows us to make a lot of meaningful statements, because saying, well, it sounds too loud to me, and the next person might say, well, I think it should be turned up more, there's not really, it's inherently subjective, and so it's a very difficult basis to move forward. And that's why we're very bad judges as humans of what is too loud. Something can sound perfectly comfortable, but it can be at a damaging level. Something can sound harsh and unpleasant, and we say, oh, we should turn that down, but it can be at an objectively safe level. So we can't trust our judgment here, and that's why SPL measurement is really important. The trick is that if you start to meter it, you realize there are a lot of different ways to meter this. So similar to when we looked at the averaging on the RTA, you saw that how there was one physical input signal, and that same signal looked a lot different depending on the different parameters we set up, depending on the averaging and the banding and stuff like that. We can make that data look different. And it's the same with SPL. So if you go get a copy of Smart and out of the box you click Start Logging SPL without changing any settings, these are the SPL metrics that we're going to log. And so the trick is that all of these are different representations of the same actual event. So here's an SPL history timeline. Time moves from left to right. Here's about 3 minutes of SPL data from a concert. And you can see that we've recorded a lot of different SPL metrics here, and they're all at different levels. So the blue one down here, the SPL-A slow, is between 85 and 89 at this moment. And at the same time, this green one up here, the peak C, is well over 110. So it doesn't make sense to say, hey, is it above or below 90 in here? And so that's why we have trouble when the manager of this venue came up to me and said, hey, keep it under 95. 95 is right here. So in order for that statement to be meaningful, we need to add a little more context than that, because 95 in and of itself, without saying how we measured it and which metric we're using, isn't enough to be actionable. So the point of this little segment is just to talk about what are the things we need to do to make our statements about SPL actually meaningful. One of them is we need to look at the frequency domain. Here are some weighting curves. You could think of the weighting curves as EQ filters that are applied to the incoming measurement data. And so the Z weighting is the green line here, and that is no weighting. You also hear it just called unweighted, but Z weighting is a little bit easier to talk about. And so the two weighting curves that you're most probably familiar with are C weighting, which is the blue line here, and the A weighting, which is the red line. And you can see that C weighting just has a little bit of a roll-off at the frequency extremes, whereas the A weighting has a pretty significant low-frequency roll-off. It's down 20 dB by 100 hertz. So with A weighting, a lot of that low-frequency energy is not included in the measurement, and so it's difficult to tell whether your subwoofers are even on or not. And these weighting curves have historical roots. We're not going to get into it. They're based on research from the 1930s that is no longer valid, and it's no longer a good description for what we know to be true. So they've sort of their basis is sort of a historical oddity at this point, but our purpose is, hey, we know that these affect the measurement in different ways, and so we just need to know which one we're talking about and which one it makes sense to use in a proper situation, okay? So for our purposes, here is the same 3 minutes of a rock concert. We can see that we have timeline data here for SPL-A slow and SPL-C slow. So the only difference between these two is the weighting curves. And you can see that the C-weighted data has a much higher value at the same instant as the A-weighted data does. And the difference is 10 to 15 dB. It can be even 20 dB in some cases. And this difference is caused by the fact that the A-weighting curve rolls off the low frequency in the measurement, and so you're going to get a lower number. And so this is a big, huge rock concert, C versus A. And we can actually look at this, and we can sort of tell, based on the difference between these two curves, it tells us about the low frequency content of our mix. So if you have a really bassy mix, you're like at an EDM festival or a dubstep festival or something like that, you're going to see a bigger difference between A and C. So it's really helpful to look at both of those metrics together. So if we look at something like human speech, for example, you see the difference between the A weighting curve and the C weighted curve. Those data points are very close together. As time goes on, they're separated by only a couple of dB, and that's because a human speech signal does not have a lot of low end, and so there's not a lot of energy falling in that lower region that's rolled off in the A weighted curve. So which weighting curve we use is going to drastically affect the number that we get as part of our measurement. So it's really important to specify which weighting curve we are using. The other thing we need to look at is what's going on in the time domain, and this is exactly like the averaging example that we looked at when we were talking about the RTA. So I have here SPL slow and SPL fast. These are all C-weighted. So if you go and get a handheld meter or an iPhone app or something like that, your two choices are probably going to be fast and slow. And what we can see is, depending on how long of a window we look at and average that data over, we get different results. For comparison, the green line up on top is what's called peak C data, and that shows us what's the instantaneous level at the mic right now. And in the same way that longer averaging times on the RTA sort of suppressed the peaks a bit, it happens with fast and slow. And the longer the measurement gets, the more integration time we use, the lower the average level is going to be, because we're regressing to that average. We're not picking up the peaks as much. They're not influencing the measurement, that is. The problem with both of these is that they're both very, very little context. C slow measurements, slow SPL has an integration time of only 1 second. And so we can't make any realistic statements about how loud this song was, or what's the level of the show in general. And hey, the city has a noise ordinance that says we can't be over 95A. So are we violating? Well, a slow or a fast on your meter, you're only looking at a snapshot in time, and so it's not a meaningful way to answer that question. So what we need to do is need to look at what the average level is over a longer period of time. So for that, we use a metric called LEQ, which stands for equivalent continuous sound level. And it's literally a running average. We're taking all the data points over X number of minutes, and we're averaging them together. And we will put a number after the LEQ to specify how many minutes we're talking about. So an LEQ 10 is a 10-minute average. An LEQ 15 is a 15-minute average. And what we can look at is, here is the blue is SPL slow. And we have an LEQ 10 and an LEQ 15 visible as the green and yellow lines. And what we can see is, once we start to average longer time periods together, it's very easy to make a statement now about what the average level of the show is and what the equivalent level of the show is. And so now we can say, okay, no, we're not exceeding 95. We're safe. Whereas if you were using a handheld meter that only had slow, you can see there are a couple points here where you probably exceeded 95, and you don't want to get fined based on one snare drum hit. That's not a fair way of taking the measurement, and it's also not a very meaningful way of taking the measurement, because it tells us absolutely nothing about the average level or how much hearing damage was sustained or sound exposure levels or anything like that. To make those statements meaningful, we need to look over a much wider period of time. Generally, we find that once you get to a 15-minute LEQ, that's a wide enough time window where you can make a really meaningful statement about what the level of the show is, but it also gives the front-of-house mix engineer some room to have some loud moments and some softer moments, some more intimate moments, while the overall level is still kept reasonable and compliant. And from there, I have a couple of slides about hearing sound exposure and what's too loud, and we don't need to all go through that. The only point I want to make here is there are two bits of guidance that we're primarily relying on in the United States. One is OSHA and one is NIOSH. The difference is OSHA tells us what is permissible, meaning your employer is liable if you go over this level. And so that OSHA is not designed to protect your hearing. It's designed to it's designed to indicate the point of liability, actual liability, when you have a claim against your employer, when they are legally obligated to do something about it. On the other hand, NIOSH, which is the National Institute of Occupational Safety and Health, they come from the Department of Health, not the Department of Labor, and their focus is actually on preserving your hearing, not damaging your hearing. And so the NIOSH recommendations are just recommendations. They're not what's permissible under OSHA. They are what's recommended if you want to keep your hearing safe. And so they're a lot more stringent. And so you can actually take a look at the LAEQ levels. It's important to use A weighting when we're talking about hearing exposure, because that is what we found is the weighting curve that best matches the actual energy range that's damaging to the human ear the most. I'm not saying that low frequencies can't damage your hearing, but what we are saying is that statistically the A-weighted data gives us a pretty good model for actual noise-induced hearing loss damage. What do you do when you've got a venue manager standing next to you with their own handheld dB meter that doesn't know about these nuances? That's a really important question, and that's sort of why I think there is becoming more of an industry dialogue about this stuff, because if you don't have a better answer, you are at the mercy of that person. And there are problems with that. I'm going to come back to that in just a second. I just do want to show that one of the features that we added to the most recent update of Smart is the ability to meter exposure directly. We can meter the OSHA or NIOSH exposure directly as a percentage, so you can put it on a meter and get a value from 0 to 100. That's your dose for the day. You can measure it directly instead of having to go look something up on a table. So let's talk about that for a second. I have a lovely slide in here somewhere. Here we go. So this is kind of just for fun, but you can see that if you buy 5 meters, you have 5 different answers to what the level is. And unfortunately, these things have a seriously wide range of deviation. It's plus or minus 4 dB out of the ones I've tested. I bought like 20 of these. I got them all in my basement. Different brands, new, old. I checked them all against a calibrator. Most of them come out low, which is good if you're trying to beat the noise police, but it's really bad if you're talking about, not damaging your hearing. A couple of them have come out significantly high. I've seen 2 dB, 3 dB high out of the package. I've seen 4 dB low out of the package. That's a problem. Put aside for the fact that most of these guys cannot measure LEQ, so if you're talking about, hey, am I violating OSHA? Hey, am I in compliance with NIOSH? Hey, am I violating my city's noise ordinance? If you're measuring SPL fast or slow, you're not even using the right metric. So as we saw in the other slide, that's not really a meaningful answer to the question. But the bigger problem here, because you can get a handheld meter that does have the logging and can produce an LEQ measurement. You're going to pay a little bit more. You need a computer under the hood to manage and average those data values and to log them. The bigger issue here is that a small error in calibration will create an absolutely enormous error in terms of exposure. So NIOSH has a 3 dB exchange rate, which means if the level goes up by 3 dB, the amount of time that you can safely be exposed to that level is cut in half. So if your calibrator, your non-calibrated dB measurement is 3 dB low, you may think you've been at a safe level for an hour, but you actually hit your 100% dose at 30 minutes. So you got twice the amount of dose that you thought. And so what we can see is that error accumulates very quickly. And what we've noticed is at 2 dB, if your error is just 2 dB, which doesn't sound like a lot, and in terms of mixing, it's almost nothing. But in terms of SPL measurements for sound exposure, if you're 2 dB off, the window of uncertainty in your measurement is as long as the event itself. So for a 60-minute event, if you're 2 dB low, you're actually going to see that you could be exposed to that level. It'll look, a 2 dB low means, hey, we just got 60 minutes of exposure, but you actually got the equivalent of that exposure after less than 40 minutes, like 36 minutes. And if you're 2 dB high, then the actual exposure time that it'll take to hit that 1 hour dose is about 95 minutes. So the range of variation is really huge. And so if you're talking about exposure and hearing protection and noise-induced hearing loss, that's a situation where the measurement really does have to be accurate. If you're measuring for consistency for night to night, hey, I want to hit the same levels with my mix every night, you don't even have to be accurate at all. You can just put a dummy value in your calibrator and just try to hit the same level. So the other thing that we can do is if you buy a calibrated meter or you have a calibrated software rig, I'll show you Smart's SPL capabilities in a second here, a calibrator that comes with a National Institute of Science and Technology, or is it standards? It's NIST, N-I-S-T. They come with a certificate of traceability and basically establishes that, hey, this meter or calibrator has been evaluated in a lab and has been found to be compliant. And so you can trust that the value it's showing you is accurate within whatever, half a dB, a third of a dB, whatever that tolerance is that's going to be indicated. So the way to know that the value is correct is that you have the paperwork to prove it. And that's sort of how you call this bluff. So this is how you can call the bluff of the handheld meter problem. Show up with a superior solution. In a legal sense, you can get that thrown out in court if they can't prove that their measurement was accurate. And so my calibrator, I use the iSimcon SC1. It comes from the factory with a certificate of traceability that it's been tested, and it shows you what the level is and what the tolerances are. And so you can produce that. You can prove that, hey, my measurement is more accurate than your measurement. And if you have a very high bar that you have to meet for a legal standard where you have to establish, SPL evidence that can hold up in court if you're dealing with noise complaints and lawsuits and fines and stuff like that, there are tamper-proof calibrated systems. One of them is called 10 Easy. It's sold by SG made by SG Audio. And you can use a tamper-proof solution like that. It's a black box that you cannot get in and tweak the gain. You cannot get in and tweak the sensitivity. And it's a very expensive system, but if you absolutely need that level of, to establish that level of compliance, you can certainly do that. So it's one of those things that you have to decide for yourself how important it is that this number is meaningful. And the more important it is, the more accuracy you're going to want, and the more expensive that becomes because you're buying precision hardware. I will pull up, this is Smart's SPL history timeline. It's 2 panes. On the top, you have whatever metric you have currently focused. On the bottom, you have all the metrics that I've selected to overlay. I'm going to full screen this. And you can see when I drop down, I can check or uncheck these boxes and show different metrics. The other thing that I can do is show a time range. If I drag this window to the right, you can see a time range on the bottom in more detail. So this dip here is where I took my break, and you can see that the fast and slow levels went down, and these sort of gentler lines, those are my LEQs. So we're looking at LEQ1, LCEQ1, and again, we're talking about a human speech signal here, so you see that these levels are within a couple dB of each other. That's the LAEQ1 and the LCEQ1, and if we look at the 10 minutes, that's an even gentler slope. And so that is a software SPL logging solution, and this is all written to a text file, and they're tiny, so it's just a line of text for every time. And I have it set to log a data point every 3 seconds. You can go as quickly as 1 second if you want, and it's a text file, and you can email it to people, and you can actually click this button and generate an SPL report, and you can print that out, and you can have an ironclad time-stamped record of what your levels were at any point in time. Of course, this is only as good as the calibration. So if you don't have a calibrator, Smart doesn't know what level it's seeing. So the calibration process is really important. And, a good calibrator can be had for $200 or $300. And again, you're going to pay a little bit more to get something that does come with the paperwork. But if it's important to establish that that measurement is correct and is accurate, you're going to need that level of precision. And, spend a little bit more and get a good one. They last for years, and the drift on a good calibrator is tiny. They drift fractions of a decibel. So that's my SPL spiel. I think that's about all I have. So I definitely want to say thanks to you guys for tuning in. That was super a lot of fun. And I don't have an ending slide. So yeah, thank you for your time. I hope you enjoyed it. I hope to post this to the YouTube channel. If there are no technical problems with that, it'll be up there, so you can go back and you can check it out and you can review it and find all the places that I screwed up, and send me some questions if you have them. Please feel free to do that. Thank you guys for tuning in, and I hope you stay safe out there, and take care of yourself, take care of your loved ones, and I'll talk to everyone real soon. All right?